All right. So, what we're going to do here is continue with chapter 5. Specifically, we are now in 5.4, which is where we look at how to differentiate and integrate exponential functions. Okay. So, up to this point, we've been focusing primarily on logarithmic functions. Now, we're going to take a look at exponential functions. All right. And I think you'll find that exponential functions are very easy to deal with. The rules for differentiation and integration are quite straightforward compared to some of the other techniques we've looked at before. So anyway, what exactly is the natural exponential function, as it's called? Um, it's actually, there's many exponential functions. When they say natural exponential, they mean specifically e to the x. Okay. Now, this graph is giving us a hint as to where this discussion is going, because you can see by looking at it, um, if I were to draw a line to the origin rather, well, you can see what's going to happen. You can see that the two functions, natural log of x and e to the x, are mirror images of each other. And since they are symmetrical to each other with respect to the line y equals x, or f of x equals x, that's how we know that they're inverses of each other. So I could write, for example, f of x equals um, log x, and that in turn means that f inverse of x is e to the x. They're inverses of each other. Okay, now that's an important detail. We're going to see a lot of the consequences of that as we go along. And of course, that being the case, if you remember, we had this discussion once before, that indicates that the domain of log x equals the range of e to the x and vice versa. That means then that the domain of e to the x, therefore, is the range of log x. Now, based on the graph too, you can clearly see that the domain for the log of x does not include the negatives or zero itself. Okay. And then you can see that, um, let me make a note here so it's clear which one I'm talking about. Therefore, the range for e to the x is the same thing. And you can see by looking at this graph that the horizontal asymptote, the horizontal axis is clearly an asymptote to this function. It never quite reaches the horizontal axis, as over here, the log x never quite reaches the vertical axis. And of course, the range for the natural log is all real numbers. And of course, that indicates that the domain is also all real numbers for e to the x. And you can see that by looking at the graph. In other words, um, there's no value of x for which this function is undefined. Down here, there's no value of y for which this is undefined. Okay. All right. So that's how they're related to each other. So now, yes. And so, of course, what they're showing you here too is they're proving that they're inverses of each other. Let's just say that f of x is log x, g of x is e to the x. We can prove that they're inverses with a technique that we've seen before. That means we have to show that f of g of x is x and g of f of x is also x. All right, let's do this. So in this case, f of g of x would mean log of e to the x, and that's true. You can take out your calculator if you want and just put any number in for x, and you'll see that this works. And then g of x is e to the log of x. And again, this brings us back to x. So this is proof that the two are inverses of each other. Okay. Um, and by the way, these are important identities. You want to make sure you remember these. These are very important. We can often help ourselves simplify a very messy problem by using identities like these. Sometimes you'll say like a very messy equation. We can make it simpler by taking the natural log of both sides, or possibly e is raised to that power on both sides. In other words, we can exponentiate both sides. So these are very important results. Here's one. So we'd like to solve for x, and there's the graph, by the way, so you can visually see that, this is what we're looking for. Um, 7 equals e to the x plus 1. Now, you might say, well, what do we do now? Well, that's what these properties are helping us with. Now, I can certainly apply the same function to both sides. I can take the log of both sides. I can square both sides. I can do whatever I want, as long as it's the same on both sides, and I won't affect the results. So here, this stays log 7. This is simply a constant. But here, I end up with x plus 1. Okay, in other words, um, so this is the more general version of what we see here. If the log of e to the x equals x, it must be the case that the log of e to the f of x equals f of x. Okay, so in other words, they cancel each other out, the log and the e to the x. So the log of e to the x plus 1 reduces very simply to x plus 1. And so I can subtract 1 from both sides. And whatever number that is my answer. All right. So, and it says here, we could check that out in the calculators if we want, approximately 0.946. Okay. Now here's some important properties with exponentials, natural exponentials, that is, although these also apply to any other exponential function too. E to the a times e to the b, because they're the same base, we can rewrite that as e to the a plus b. And when it comes to division, because obviously both of these have the same base, we rewrite that as e to the a minus b. But again, remember, this would apply no matter what the base is. It could be any number, 2, 7, 15, it doesn't matter. Now, here's some key properties. Now, this is the graph, by the way. You notice how it has this very special shape to it. It starts out very slowly in the second quadrant, and then it starts to grow. Once it gets into the first quadrant, it starts to grow very quickly. And if you notice, the intercept is the point 0.01, because um, since f of x is e to the x, f of 0 would be e to the 0, which is just 1. Okay, so let's see. Let me just do one thing here. I just want to put a label here. All right, so that's the first one. Then they're going to tell us that the domain, as we mentioned earlier, is the entire real number line. You can see as you look across the horizontal axis, there's not any discontinuities. And no matter what number I plug into this function, it's not going to give me division by zero or an imaginary number. Okay. What else are they trying to tell us? The range is zero to infinity. And again, we've already seen this. And that's because x equals zero is a horizontal asymptote. I'm sorry, not x equals zero, y equals zero. In other words, the horizontal axis um, is a horizontal asymptote of this function. And so therefore, if you remember, the way this works is the round parenthesis or brackets means that zero is not part of the range. It goes for everything from slightly above zero to infinity. And you can see by looking at the graph, once we get, as we get x keeps increasing, the function will grow forever. And in fact, it'll grow very quickly forever. This is a very rapidly growing function once it gets started. Once we get into the first quadrant, it starts to grow very, very quickly, like all exponential functions. Oh, here's another thing they want us to know. The function is continuous. And you can see just by looking at it, there's no breaks. And increasing, which of course means that as x goes to f of x increases continuously, right? And one to one. Now, how do you know just by looking at that graph? You might recall we introduced a while back the horizontal line test, meaning that no matter what horizontal line I draw through it, it'll never cross that curve more than once. Okay. And what does that tell us? And once again, just a quick reminder, this guarantees the existence of an inverse. And of course, we already know what it is. And that, of course, is natural log of x. All right. What else do we need to know? The limit as we go to negative infinity is zero. As you can see, as we move in this direction. And as we go to the positive direction, here we're going, as we go down to negative infinity, the function goes to zero. As we go to positive infinity, the function goes to positive infinity. Okay. So those are the next two properties we need to know. Okay. Is that it? Let's see. What else do they have for us? Yes, that's all of them. Okay. That'll do for now. All right. Now, finally, we get to have some fun with this, the derivatives of the exponential functions. And I mentioned before, these are very straightforward formulas, more so than maybe any of the other derivatives formulas we've seen. Look how easy they are. The derivative of e to the x is e to the x. Well, you don't see that every day. And then for if we make it more complicated, e to the u. Now this is because of the chain rule. It's e to the u du. Okay. So we have to keep that in mind. Remember, as always, u is assumed to be a function of x. Okay. All right, great. Well, that was it. That's all we needed to know. So, we have some examples. Let's try these. All right, here we go. D dx of e to the 2x minus 1. So we'll let u equal 2x minus 1. Um, actually, we don't need the du part. It's just du dx. That's fine. What happened here? Uh, hmm. I always have to check, when I'm writing like this, very occasionally, just the slightest touch on the keyboard, and I could erase all of it. Looks like some of the stuff did get erased. All right, hold on. So therefore, since this is an example of e to the u, that means the answer must be e to the 2x minus 1 times 2. Okay, or you're going to write it like this. That would be much more normal. Okay, and that's because u is a function of x. We do need to include du dx. Beautiful. All right, number two. E to the minus 3 over x. All right, e is minus 3. U is negative 3 over x. It's probably easier to write it as, x to the minus 1. So then du dx would be, based on the power rule, for derivatives, that is. Okay, sorry, nx to the n minus 1. And then that means here we're going to have, oh, and if there's a constant, they separated these two rules in the slides. Let's do this. Cn x to the n minus 1. All right, so the c, really just the c is a constant. It's just being attached to the answer here. So therefore here, what do we have? Negative 3, negative 1 x to the minus 2, or positive 3 over x squared. So therefore, the final answer will be, based on this result, e to the minus 3 over x times 3 over x squared. And they changed it slightly. They wrote it as 3e to the minus 3x over x squared. Of course, it's the same thing. Beautiful. All right. Now, what about, see, now this one requires the product rule. So we have to keep an eye on it. What do we have? X squared e to the x. All right. So let's just quickly refresh our memories about the product rule. All right, so it's the first times the derivative of the second plus the second times the derivative of the first. So up here, you could think of this as f of x. And so f prime of x is 2x from the power rule. Here's g of x. And of course, because this is such a simple derivative, it's g prime of x is also e to the x. So here's what we're going to do. We'll plug these in to the product rule formula. All right, so once again, f of x is x squared. G prime of x is e to the x. G of x is e to the x. F prime of x is 2x. And we can simplify this a little by writing. And that's it. We're done. Yes. Oh, see what they did. They decided to factor it out one more time. Not that it makes any difference, but they're the same thing, of course. And then, of course, we have a quotient rule. Let's remind ourselves how that works. All right. So we have this function. All right. So f of x is the numerator. Oops. That's it. All right. And of course, that means that g of x is the denominator, e to the x plus 1. Now, keep in mind, this one is e to the u. So if we let u be 3x, du dx is 3. So f prime of x is e to the 3x times 3. Because remember, this equals e to the u du dx. Now, g prime of x, on the other hand, is even a little bit simpler because you're differentiating e to the x, which is just e to the x, plus the 1 has a derivative of 0. So these are our final results. So once again, I'll write up the quotient rule, and then we'll make the substitutions. All right, so let's substitute. G of x was e to the x plus 1. F prime of x is 3 e to the 3x. F of x is e to the 3x. G prime of x is e to the x. And again, g of x is e to the x plus 1 squared. Okay. Um, Now, I know that they went ahead and they simplified this like crazy. Not really. Let's just see what we can do. We'll multiply these out. By the way, remember this rule. E to the a plus b So that's what's going to happen here. I'm going to have 3 now. E to the x times e to the 3x will therefore be e to the 4x. Actually, now I'm out of space. Let me move this. So in other words, and then we have the 3. And then for the second one, same thing. We've got e to the 4x. And then we divide that by e to the x plus 1 squared. What do you know? We've got 2 with the same base. So we end up with 2 e to the 4x over e to the x plus 1 squared. Oh, see what they did. Hold on a second. I've got 3e to the 4x. Oh, you know what I did? I left one of them out. Okay, hold on one second. I just noticed it now. Let's fix this. Yes, there's a term missing here because yes, these when these go together, you get 3e to the 4x, but I forgot about this part here. There you go. And then over here we have e to the 4x. And then they factored out e to the 3x from both of them. And now we're all set. All right, good. So where I goofed it up is when we multiplied these two together, I left out this piece. All right, now we're all set. All right. All right, let's see what's next. Find an equation of the tangent line. So you know they're going to want a slope here to the graph of f of x equals 2 to the plus e to the 1 minus x. E to the 1 minus x. All right, we'll start by taking the derivative. Now keep in mind, for this one, if we let u be 1 minus x, du dx is minus 1. So we'll end up, the first one will just be 0. So all we need to deal with here is that e to the 1 minus x. So we're going to end up with minus e to the 1 minus x. And then they want us to find the tangent line at the point 1 comma 3. And so here's the graph. And we're going to solve for this at evaluate f prime of 1. So we replace the x with 1. And that gives us minus 1. So at that point, the slope is negative 1 of the tangent line. Actually, I'm going to copy this graph. It's going to be hard to draw it. All right, so there's our point, 1, 3. There's our function. And we know that the slope of this line, because it's the tangent, is negative e to the 1 minus x, which means here that gives us um, -1. So that means we know two things about this tangent line. Number one, it contains the point 1, 3. And it has the slope. That we just solved for -1. So we're going to use not the traditional y equals mx plus b format, meaning the slope-intercept form, but the one you don't see as often, which is we call this the point slope form, and it contains the point x1, y1. And so we plug that in. That point is 1, 3, by the way. And of course, we know the slope is -1. Or we can write it as, and then we can rearrange it. And that is the slope of the tangent. Sorry, it's the equation of the tangent line. And that's it. We're done. We've had problems like this one before, but this is the first time we've done it with an exponential function. That's the only difference. All right, now integrals. Well, if we know how to differentiate exponential functions, we need to also integrate them. And again, the formulas will be surprisingly simple. Well, here they are. This is all you need to know about the integrals of exponential functions. Look at that. The integral of e to the x dx is e to the x plus c. I mean, it makes sense. If you differentiate this, it'll just bring you right back to e to the x. Okay. And then for u, same thing, just e to the u plus c. If I differentiate both sides, you'll see that I get the same thing. Wow. All right, here we go. Integral e to the 3x plus 1. Now, it says here dx. So that would be this case. And so du dx is 3 dx. We don't have that, but we can provide our own constant. So here's what we have to do. Okay, so now we're all set because this is e to the u and this is du, because we do have 3x and Oh, what did I do here? I sorry, this should have I wrote the wrong thing here. It's not 3x, it's 3dx. That's better. Much better. All right, here we go. So now, following the rule, we have, and that's it. We're done. Hmm. It's that simple. Okay. Or they wrote it like this. It's the same thing. All right, good. How about this one? All right, now this is a definite interval. We haven't seen one of these just yet, but the rules are exactly the same as what we're used to. E to the minus x dx. So u is negative x, du dx is negative 1. So that means that du is negative dx, which we don't have, but we can provide our own negative by multiplying, and we're basically multiplying twice by negative 1. So we have, but before we continue, remember, because this is a definite integral, we must replace the limits of integration. So notice we can't use 0 and 1. So in other words, if I rewrite this as e to the u du, these have to be functions of u. So u is defined as negative x. So when x equals 1, u is negative 1. When x equals 0, u equals 0. So basically, we're going to take this and rewrite it as negative 1 to 0. And of course, u, this leaves us with, okay, so then we can have e to the 0 minus e to the minus 1. This is 1 minus e to the minus 1, and that's it. We don't need a constant because this is a definite integral. Right. Or, you can rewrite this as 1 over 1 minus 1 over e, which is approximately, according to this, 0.632, if we need to know. And if you can see from the graph, that's what we're looking at. So the key to the whole thing, which is easy to forget about, is to, when you use U substitution, make sure you change the limits of integration. Okay. It's easy to forget about that. All right. Here's another fun one. Oh, what do we do with this one? Well, you know what? Here, let's try this. Now, here, there's a couple of possibilities. If you get it wrong the first time, you'll just end up making a big mess. So you'll know you've got it backwards. So let's try u equals 1 plus e to the x. Now, of course, the derivative of 0 is just, of 1 is just 0. So if you rewrite this slightly, You can see that what we have here is du, and this is 1 over u. So this is what we have. Oh, and one more thing. We still have to replace those limits of integration. So when x equals 1, u equals 1 plus e. When x equals 0, u equals just 1 because that would be e to the 0. Oh, sorry, 1 plus 1. I almost blew it. 2. Okay, there we go. So we ultimately end up with, all right, so we've established the upper and lower limits of integration when we have u instead of x, that is. So again, when x is 1, u is 1 plus e to the x. When x is 0, u is equal to 2. And you can rewrite these now as 1 over u du, or if you prefer, oh, sorry, this is not e to the x, it's just e. These have to be constants. Okay, and you can rewrite this as du over u, which means it's the natural log of absolute u evaluated between 1 plus e and 2. All right, so we evaluate it as following. Based on the fundamental theorem of calculus, we just substitute and subtract. And since both of these are positive constants, we don't need the absolute value signs. So we can leave it like this: log 1 plus e minus log 2. And that's it. We're done because this is a constant. If you want to look it up in your calculator, you certainly can. The log of 1 plus e is approximately 1.31326. The log of 2 is approximately 0.69315, let's say. And then that's going to leave us with approximately 1.31326 minus 0.69315. It's about 0.62. Okay, so what we have is fine, but if you need to know the exact value, there it is. It's approximately 0.62. So in the graph, you can see what they're actually doing here is they are integrating this function, which looks kind of like a straight line, but not exactly, over the interval from 0 to 1. So the area, that shaded area there, is that 0.620. Oh my God, what about this one? Okay, so what's going to happen here is that we're going to use u substitution in the following way. Why don't we try this? Let u equal e to the x so that du dx is e to the x, and du is, of course, e to the x dx. So if you rewrite this a little bit, you'll see that we have what we need to write this as the integral from -1 to 0 of cosine u du. And if you look at the basic rules of integration, we have a chart in the slides here somewhere. That's going to give us sine u evaluated between, oh, wait a minute, we almost forgot to do the transformation. Hold on 1 second. Because remember, we're doing a definite integral. If we're going to let u be e to the x, when x equals 0, u is e to the 0, which is 1. And when x is -1, u is simply e to the -1. So we have to replace these limits of integration with 1 and e to the -1. Okay, so let's do that. Now, if this was an indefinite integral, we would have wound up with sine u plus c, but instead, we'll end up with the sine of u evaluated between 1 and e to the -1, and we'll get, and they're both constants, so we're done. Okay. And according to this, they went ahead and calculated it for us. This is approximately 4.482. So here, the tricky part was recognizing that this is u substitution, specifically that we should let u be e to the x. If we let u be cosine e to the x, we would not have gotten our result. So, if you tried that and you got it wrong, you could go back and try it again. But the bottom line is, if you pick the wrong u with u substitution, you'll know it because you're making your results much messier rather than simpler. Okay. All right. Well, what else do we have? Here we go. Let's try this. Now, first, let's get all the like terms together. We'll add that constant to both sides. Divide out the 7. Now, remember, we did this before. We can take the natural log of both sides. And now we've got 3x equals the natural log of 15 over 7, which is some constant. And we end up with x equals 1/3 log 15 over 7. And that's it. We're done. Which one is that? 1/3? Yeah, it would be A. All right. And then what about this one? Now here we're going to need a product rule, of course. So remember how that works. Let's review really quickly. If we define h of x to be f of x times g of x, then h prime of x is the first times the derivative of the second plus the second times the derivative of the first. And so here, you can think of this as x to the sixth e to the x. This would be our f of x. And then using the power rule, we have 6x to the fifth. If g of x is e to the x, then g prime of x is also e to the x. So when we plug everything in, let's see what we get. F of x, x to the sixth, e to the x. And then, we can simplify this or, gather the like terms. This will do the job. Okay, so that's going to be, oh, it looks like they just left it like this. Or Oh no, it must be C because see what they did was they factored out. Yeah. So in other words, here's what they did. They factored out x to the fifth and then rewrote it as x to the fifth e to the x times x plus 6. And that makes it C. Okay. Beautiful. All right. So that concludes 5.4. What's coming next? You ask. All right. Let's take a look and see what's coming. Oh, bases other than E. All right. So in other words, these are exponential functions with other bases besides E. So the rules are a little bit more complicated here, unfortunately. The E makes things very nice for us. Like here's an example of what I mean. Um, A to the x equals e to the log ax. So when we use the rules that we just did with a to the x instead of e to the x, there's going to be a lot of chain rule results that may not be expected. So it's going to be a little bit messier than what we've done up to this point. So there's a handful of definitions that we need to know very well in order to avoid getting confused in this section. Um, so let me just write a list of them real fast so we can just get a head start on this. And we'll get to these all as we go along. I just want to list them right up front, and then we'll come back to them as we need them. So we start by writing, as the one we just saw is, okay, we also have log AX equals 1 over natural log A times log X. Okay. Or if you prefer, you can write it like this. Okay. And of course, they're making the point here that this is true no matter what A happens to be. In fact, I think we mentioned this once we were looking at the calculators and realizing that they only have the natural logs and the common logs. What do you do about the others? For example, log base 2 of 8 equals 3, since 2 cubed equals 8, but we also could have done this. And if you go to your calculator, you'll see that that does in fact give us 3. All right, once you try it. Yes, it is. It's 3. So this will work for every base. Okay. But we've run into this one before, maybe without realizing it. Okay. Um, so what else do we need to know? There's actually not that many. A raised to the log a x power equals x. Interesting. Um, and conversely, log a of x, not x, a to the x equals x. And then here's an interesting one. Oh, actually, we'll save that for later because it involves an integral. But these are the ones, these are identities that we need to be comfortable with so that the rest of what follows makes sense. Okay. Yeah, so these are the ones that we should know. And we'll refer to these as we go along. All right. But then keep in mind that when we remember how easy the derivatives and integrals of e to the x were, they'll be a little messier here, but not much. Okay. So anyway, um, some key properties. Now, these I'm sure you're already familiar with. These are the standard laws of exponents. As long as a with the same base, any base a to the zero power is one. Here's the product rule: a to the x times a to the y equals a to the x plus y, because they're the same base. A over, this is the quotient rule, a over to the x over a to the y is a to the x minus y. And then this last one is the power rule for exponents. A to the x raised to the y power is a to the x times y. Okay, so these are, I'm sure you've run into these before, but it's good to review them. So they want to show us this half-life model. The half-life of carbon-14. Every time you hear about carbon dating, this is what they're talking about. They know that the half-life of carbon-14 is 5715 years, which means it takes that long for the sample to be reduced. The radioactive material is reduced by 50% in 5715 years. So if we had a gram of carbon-14, how much will be left in 10,000 years? Okay, so let t equal the present time. Y is the amount in grams of carbon-14. So here's the model they want us to use. Um, that's whatever this element is. Oh, sorry, it's carbon-14. This is how we define its half-life. The amount that's present, given that t equals 0 is today, as we go further into the future, we can figure out how much is left in our sample. So, for example, let's say we wanted to know how much is left in 100 years. Oh, let's find out what that is. 0.9879, which means 98.79% of the original amount of carbon-14. So let's say we tested some object or other and we found that it has 0.9879 grams of carbon-14. That would indicate that it's 100 years old. Okay. Oh, you've seen these on TV. You've seen these in movies. It works very well, but it's really meant for extremely old objects, not like things that were within the last century. Like this is how they can tell how old the pyramids are and that kind of thing. Okay. So when we go out 5,715 years, then the exponent is one, and that means half of the radioactive material is left. Let's see. When T is 11,430, that will bring us down to a quarter. And this is the plot that tells us this relationship. All right, let's take a quick look at it. Yeah, so you can see if it's decaying very, very slowly, okay, very slowly. It takes 5,715 years to reduce the total amount by a half. So yeah, that's very slow. Okay. Anyway, so this one we just got through looking at. Log AX is the natural log of X over the natural log of A. Um, log A1 is 0. Now, by the way, this just means log with any base. It doesn't matter which one it is. It could be E, by the way, but you can see these are the exact same properties we've always had with logs. The log of A x to the n is n log A x. The log of a product is the sum of the individual logs, And here we can see that the log of a ratio is equal to the difference in the two logs. Um, oh, here's something else they added. Let's add this to our list. I guess we'll have to put it down here. F of x equals a to the x. G of x is log ax. F of x and g of x are inverses. And I'll put in parentheses here, just like as we saw earlier, and you can see it's the same thing, except that the base is e instead of just some a. But a can be anything. It could be any constant, and including e. If it is e, then it becomes this expression. Okay, but they just want you to see that it works for all bases. What else do we have? All right, so wasn't that part of my list? Hold on. Oh, what happened to my list? I went right past it. Hold on. Here it is. Um, A log A. Yeah, no, this isn't here. We got it. All right. Whoops. All right. So now what? Don't forget, by the way, if you weren't aware of it, log base 10 is often called a common log. That's what you would have used in high school science classes. So A could be 10, and that means these are common logs, and the rules would be exactly the same. Here's an interesting question. 3 to the x equals 1 over 81. What do we do now? All right, so clearly there we need to solve for x. Okay, well, what we could do is recognize that 81 is 3 to the fourth. 1 over 81 is 3 to the minus fourth. Okay, so therefore, x must equal negative 4, right? So therefore, the answer is negative 4. The other option, if you didn't recognize that, you could have done this. You could have taken the log base 3 of both sides. Now, as we just saw, remember the general expression of this was log a of a to the x is x. Where's that? Um, there it is. This last one, log a to the x is just x. Uh-huh. So in other words, you can see how that can be useful. I can solve a very scary looking problem by taking the log base 3. This reduces to x. Now, I know this is negative 4 because this is equivalent to saying, and that means I have negative 4. All right. Um, how about this one? Log 2x equals negative 4. Now, this is just a straight ahead definition. This is what, because this is a log, this implies that 2 to the minus fourth equals x. We don't have to do anything. This is how logarithms are defined. All right. So in other words, it's 1 over 16 because what it's basically telling us is that 2 to the minus fourth is 1 over 16. All right. Let's see. What else do they have for us? Differentiating and integration. Now, I mentioned this earlier. This is going to be a little bit messier than what we just saw with e to the x, but we can get used to it very quickly. All right, here we go. So, I guess I'll copy these into the notes. So, just as a quick reminder, I'll put these on the side. So, without realizing it, the e to the x is simply a special case of what we're seeing here because watch what happens. That's just one. So, in other words, this is what we were doing behind the scenes, but because log e is just one, um, we end up with this result. Okay, so you can go to your calculator and double check log base e or log of e is one. Okay, so we really were doing this before without realizing it. Okay, now how about the others? Let's try number two. And again, well, let's take a look at the equivalent version with E. And of course, um, the A, log A, becomes log E, which is 1. So this drops out. And that just leaves e to the u du dx. Oh, I'm sorry, I left this out. And so that's why it's the same thing, except that you need to explicitly write the log A because it's no longer equal to 1. Number three, let's see. And again, it's the same thing. So in other words, if that was an E, it just goes to 1, and therefore it's the same thing. Okay. And finally, this one. So remember the equivalent with E. So everything's the same. It's just that this has to be here because the E would make that into a 1, but we don't have E, we have A. So it has to be explicitly mentioned here. So yeah, things are a little bit more complicated now. All those log A's have to be there that did not have to be there before. Okay, so we'll have to keep an eye on that. Yes, it's a little bit more complicated, but we can handle it. All right, like this one, y equals 2 to the x. What do we do with it? So here a is 2. And so we're going to use which rule? Here we go. The derivative of a to the x equals log a to the x. And since a is 2, That's what we need. Okay, that's it. That's the whole thing. So those rules, we don't want to lose track of those rules. But again, it's very similar. If this had been e to the x, well, we would have simply ended up with e to the x. Ooh, how about this one? Y equals 2 to the 3x. And now this 3x, because it's a function of x, not just x, we're going to call that u. So let's find that rule. Here it is. And so, and of course, du dx will be 3. So what do we have? Log 2, 2 to the 3x times 3. Or, the book might read it like this to make it a little neater. 3 log 2, 2 to the 3x. Okay. Wow, what else do we have? Oh my God, look at this disaster. Log 10 of cosine x. So, we can think of this as log a of u, um, and that would be this one. So we'll define u as cosine x. Du dx is the negative sine of x. A is the 10. So I think we have enough. 1 over log 10 times u, which is cosine x, times negative sine x. Or to make it a little neater, okay. Whoops. Let me just neaten it up a bit. All right. Now it looks like a mess. Oh, and by the way, guess what they've decided to do to have some fun with us? They'll remind us that sine x over cosine x is the tangent of x. So they've decided to take advantage of that. And now it becomes instead negative tan x over log 10. Okay. So what else? Oh my God, what do we do here? Now, here, what they're recommending you do is don't just go ahead and start taking derivatives. Don't use the product rule unless it's necessary. Sorry, in this case, the quotient rule. Instead, try to take advantage of the properties of these logs. Specifically, the quotient rule for logs. And so with this disaster, what do we have? Well, let's see. Oh, the other thing to remember is that log a of x to the n is simply n log a of x. We might need that one. And so that radical x probably should be written as, and then of course, remember the derivative of log a x. Let's go get that one back. Wait, um, log a u, I should say, this one will be applied to both terms. Okay, so let's copy this down here. All right, what do we have? So A is the 3 in both cases. Here, oh, I just realized this is not right. This should have been regular x because we've already, that 1/2 is there because it's the square root. That's better. I think I goofed it up here too. Yeah, beautiful. Let's fix that. So the derivative of this, which is what we're ultimately after, so we factor out the 1/2. And so again, remember here we're thinking of u as the x, a is the 3. And then du dx would just be 1 in this case. And then this one, um, so this is our u, du dx would be the 1. This is a, this is a. So the second term, which I have to move down here now, is 1 over log 3 times u, which is this 2x plus 5, times du dx, which is actually 2 in this case. Well, we got quite a mess in our hands, don't we? All right, let's see if we can clean it up a bit. I don't know if there's anything else we can do to simplify it. Oh, well, they decided, I mean, yeah, we're good. We got 1 over 2x log 3 minus 2 over log 3. Yeah. So then they decided to simplify it like that. That's fine. We'll just leave it like this. Now, integration, um, oh, now actually, we haven't done this one yet, have we? No. This is our first time with integration of non-E bases. Very good. Let's see what we get out of this. Oh my God, look at that mess. Actually, let me do something here. But again, you'll see if you replace the A with an E, um, it's the same thing. It's just that the log A, E, if that was an E, it would be one. So that's why it is the same thing. This is E to the X is a special case. All right, so let's see what they want us. Here's a simple one. So A, of course, is 2. Wow, that's all there was to it, huh? Yeah. Ah, now here, this is, we already knew this. This is just review. The power rule, the general power rule. Yeah, we haven't forgotten these. We see them all the time. So what they're showing us here is some special cases. Well, this we've seen. This one looks surprising at first until you realize e to the e is a constant. So that's just 0. But look at this disaster. But keep in mind, e is just a constant. So the derivative of x to the e, as strange as it looks, that's all there is. That's all there is to it. Because if it was x to the n, you would have had n x to the n minus 1. So it's the same thing. It's just a different constant. All right, what else do they have for us? Ooh, x to the x. Wow. That sounds scary. Now, this one's going to, by the way, involve logarithmic differentiation. So, we've done this before, but not quite with this kind of application. So, what they're going to do is say, listen, first take the natural log of both sides. And then um, rewrite this. And now, when you differentiate log y, it ends up being y prime over y. We did this once before, but might have been, it's probably been a while. So you're going to get, first, we're doing this. So on the left-hand side, we have y prime over y. On the right-hand side, we have a product rule. Now, of course, if you remember the product rule, we're going to have the first term times the derivative of the second plus the second times the derivative of the first, which simplifies to 1 plus log x. Now we multiply both sides by y, and then we go back to the original definition of y, which was x to the x. And that's it. We're done. All right. So we still have a bit of some more applications here. I'll tell you, I don't want to rush through this part because it's quite interesting and it involves, unlike what they usually do with physics, this one actually involves economics and finance. In fact, it involves savings accounts and how your interest grows over time, which I think you'll find very interesting. So I think what we'll do is we'll save this one for our next session. I think we've already gone over our time limit anyway. So we'll stop here. And then next time we'll finish this up and then go on to the next section. So I think we've had plenty for one day, and I'll see you next time.